Let us start with this premise. Well, my name is Purnendu, and I will be having the first part of this course today. Me and Subhiksh, we both will cater to this course. And the premise to start with is the greatest value of a picture is when it forces us to notice what we never expected to see. So that is what data visualization is all about. This quote was from John Tuckey, who is a pioneer data exploratory data analyst. Now, I will start with a few examples so that this particular quote has its mention. In in 1854, there was cholera outbreak in London, and the germ theory was not yet discovered, so they did not even know that why the deaths are occurring and why the disease is spreading. So there was one man called statistician called Jon Snow. What he did, he collected data of addresses of people who died in this pandemic. So what he did, he took the map of London and plotted it like this. These horizontal lines, small lines, these are the for each death he plotted one line here. So what he observed after plotting, this is a small part of the original uh, map that we had. So I have cropped it and I have adjusted it so that we can visualize it better. So what he did, he plotted the number of deaths. So this many, like there are 5 deaths in this particular area. So what he found out that this particular area, this locality has maximum number of deaths. And then there was this pump which he thought was the cause of a spread of the disease. And then when this pump was removed, drastically the number of deaths reduced. So there was one map and then one pump and the outbreak stopped. So that is what the power of data visualization is. And that is why it is so important to visualize the data. It helped solve a big pandemic that time. In COVID times also we have seen a lot of data visualization papers and a lot of websites that visualize data and how the outbreak is happening and all. The first one was this by Jon Snow. And the second and a bit infamous example that I would like to take is this. In 1986, there was a mishappening uh, in a space shuttle. So just after 73 seconds of launch, the Space Shuttle Challenger exploded, which killed all 7 astronauts. So, such a big mistake by such a big organization is not a very good thing. Like, so what happened is there is something called O-rings in the space shuttle, which prevents the leakage of fuel. This is the piston and O-ring and the housing of, and then it is like a gasket in pressure cooker and all. So it prevents the leakage of fuel. It is a rubber type thing or some other kind of material, and it is sensitive to temperature. If lower the temperature, it becomes brittle and uh, that does not perform very well. So they had all the data. Without data, they will not be proceeding. But somehow they missed to visualize it. So this was a graph which was not there, although data was there. So this shows the number of O-ring that damaged on different incidents and the temperature in degree Fahrenheit. So at higher temperature, no, no O-ring were damaged. When the temperature decreased, so the number of O-rings that damaged increased. And this was at 31 degree Fahrenheit was the temperature at which the launch was being done. It was done in winter. So just imagine how many and how quickly the O-rings were to be damaged. So this all data was there, but it was not visualized right. So these two examples would have given you an overview of why data visualization is so important. So now coming to some kind of one more situation, like there can be multiple data sets with all the same statistical properties, but they can tell you different stories. Is it possible? Yes or no? Okay, so we will see. There was a statistician called Francis Enscombe. So he answered this particular question. His main motive was in those times the statistician community, they thought that descriptive statistics was all that should be, and the visualization part is just for the show off and all. But then Anscombe showed made four very small data set and showed how the different data sets, although having all the same descriptive statistics properties, tell you different stories. So we will explore this in a live notebook. And just before that, let me help you start with code setup. This is the course page. So you go to this data visualization code day, code one, and you just download it. And then, so in this, you can see different folders like data sets, docs, and this PyProject.2ml. So this is the configuration for all the libraries that you will need. And the notebooks that we are going to discuss is here, docs and inside notebooks, right? So the first notebook that we are going to discuss is this one. And these two notebooks will be discussed today. So let me, if you are using VS Code or something, so let me help you start with it. So let us just open that folder and I will help you start with it. I'm giving this so that you might not feel any difficulty later. So when you are here, so the first thing is to get into a terminal, right? Okay. So you need to install this UV, right? For installing UV, there are a set of steps that you can find easily. And if you would like me to give you like uh, the set of steps, then in your uh, whatever OS you use, you can use it and install Mac OS and Linux. So you can do this, and it will easily install. Or in on Windows, you can run this command. Okay. Oh, so I already have it installed. So just make sure that you have this pyproject.toml in this particular directory where you want to do the uh, whole project, right? So UV, just you have to put uv.sync. Let me first give you what it is in there. It's so it will have some uh, basic configuration for the project, right? The required libraries, and we are using this as we learn bootcamp, which is already available in UV sync. So that is what we are using. So what you do is just UV sync and see how quickly it installs everything, and you are ready to go. Now you are ready to go. Now you this is a new uh, directory that has been created .venv, which is the virtual environment, right? So now you need to activate this virtual environment. So for that, so source .venv bin activate. You can do this. Now you can see this data visualization here. So which shows you what environment we are in right now. Okay. This is the set of steps that you can do to set it up. And now go to docs, notebooks, and this the first one. So now you can start with running with it, right? Start with the notebooks. So the steps will be a little bit different for Windows, right? Which I think you can easily figure out, or just the I think that just the difference here it will be there. Some small difference will be here. So if you face problems, you can put in the Discord, and we will help you out. This part of the code run support. This will beautify the the look and feel, but that works when we are using not using VS Code for Jupyter notebooks. We are using it on the browser, right? So anyway, we will run this. Now you will have, let me demonstrate it. You have to select the kernel for this Jupyter notebook, Python environments, and this is the particular environment that we want to use, which is this one. We inside this V and V bin and Python. This environment we are going to use, right? First time it will take some time to load the to run the first block of code. Are you all with me? I think the pace is okay, right? So I have done this already with me. So now here it will take less time. So Francis Anscombe, so he gave this very simple data sets, right? X, which is this one, Y, Y1, Y2, Y3, X4, and then Y4. So what you see, we are converting this into X and Y, this into a dictionary and converting into a data frame. So lists to dictionary to pandas data frame, and this data sets is a list of data frames. Okay. So what we other than mean and others, so we just to recap, standard deviation X Y correlation measures the strength of the relationship between X and Y. Intercept, when X equal to 0, what should be the value of Y, and the slope, like the rate of change of Y with respect to X, and R squared, the tells you the variance in Y that is explained particularly by X. So higher the better, right? So we have just given named these four data sets. So data sets have been created here, and we have named these four data sets: one Romans 1, 2, 3, and 4. And then these are summaries that we want to talk about. So we did some linear regression on it, on the data set, and predicted some and found out some values. So now we are having this value, right? The data sets, although they are much different, right? The values are different. They all have uh, same, or I mean very less difference between their descriptive stats. So mean is same, mean X is same, mean Y is same, standard deviation of X, Y, correlation. You can see some minor changes, but most of it is same. The slope R squared, and some are squared error. So all of them are same, right? Or similar. So the best fit would be described by Y equal to 3 plus 0.5x. So this is the regression line. Oh, so that should describe the data. Now we are just trying to plot it, just to find the difference between the data set, how the descriptive statistics looks to us, and what is the actual data set. So when we plot it, we are just doing a simple scatter plot, right? And the data set is like this, right? This is the Y equal to this line, Y equal to 3 plus 0.5x, and the for data set 1 and the different points. So this is a different story, and this is a completely different story, right? This is some kind of looks some kind of a quadratic equation. And then this is something else, right? And this is completely different. Just because of this one outlier point, we have this line of regression. This shows you why this again reinforces, like, why do we need to have visualization of whatever data we have, right? So now this first part is okay. So then we also, if you plot the histograms, then that also gives you a very different story, right? When you plot the histogram, the data set 1 is like this, when the most of the values have a similar kind of frequency. In some follow some pattern, and like some is skewed, right? Some one is skewed. So this is how it is like. The main crux behind it is we need to have data visualization, even if we do descriptive statistics in detail. So that is from my side. Now I would like to invite Subhiksh to give you an introduction to the data source. Over to you, Subhiksh.
So as Purnendra was saying, we see that we have four quite varying data sets, which is being fit by an approximately same line of regression, right? You can see that the slope of these lines are approximately the same. However, that these points have different locations. Now, what does this say? It says that when we have all these parameters, all these descriptive statistics, which includes mean x, mean y, standard x, standard y, that is standard deviation for the variable x, y, correlation between the two variables, the intercept, the slope, r squared, and sum of errors, some squared errors. All of these, they can remain the same, but still have a slightly varying data set, isn't it? When the data set is quite varying, even then we can have the same statistics. But what if we have the same statistics, and is it possible to have a very different kind of plotting? I would like to know from you guys. What do you think? Can we have a widely varying data set? Here we see that the same statistics is being given by a quite similar data set. How much can this data sets vary? Anyone? So to push the limits of these varying data sets, we are going to look at the Datasaurus dozen, where we have 13 different data sets. As you can see, we have these many data sets over here, and each one of these, okay, they are going to have the same mean of x and y, standard deviation of x and y, correlation, and all the other parameters as shown previously. May not be up to the fourth degree, but the first 2 degrees for sure are going to match. And this would again mean that they have somewhat similar visual representation, right? However, it's not. So the Datasaurus dataset, it starts with the Dino dataset, where you see that it really looks like a dinosaur. So you would assume that the other 12 datasets that are present in this are going to have a somewhat similar looking visual representation. However, that is not the case. You would be surprised to see how it looks when we plot all of them. Uh, so as you can see here, we have 12 other data sets which give the same statistics as the dinosaur that we showed before. Don't you think that these are just horizontal lines? These are just vertical lines placed in some place. Here we have an X-shape, circle, dots, star, slant up, slant down, bullseye, white lines. They have completely different visual representation, but at the same time, they exactly give the same statistics. The descriptive statistics are sharply something which we consider to represent the details about a particular data. We always say, we have this saying that maths is always accurate, and it's not gonna lie, right? But this is not a situation where it's lying. However, it's not enough in this case, where visualization is the only way where we can understand the true essence of a given particular data. What do you guys think about this? Do you have any doubts? So let's go to the next part of this course, where we'll be starting with the basics of plotting and using matplotlib. So before we do that, I would like to start with the different levels of analysis. So we have three levels of analysis. These are all statistical terms, the levels of analysis in statistics. So the first would be univariate analysis. then bivariate and multivariate analysis. I'm pretty sure you guys are like, what on earth is this? What is univariate, bivariate, and multivariate analysis? This guy just showed some graphs and they just represented the data. Then what is this? Where does this come into the picture? So let's go to univariate analysis. Univariate analysis is the most basic form of statistical data analysis technique. So what do you mean by this? When you have just one variable and we want to represent that in the form of any type of plot, we call it as univariate analysis. So it doesn't have any kind of a cause and effect relationship in the data. What do you mean by that? So let's consider something like we have a classroom, okay, with around 50 or 100 students, and we have the names and the corresponding height on a given data set. So, of course, there's no correlation between the name and their particular height. They don't. So, what do we have? Just the heights, right? So, what can we do with this particular height? We can plot how many guys are 5 feet 8, how many guys are 5 feet 10, how many guys are 6 feet. So, we have a frequency plot or a box plot or a histogram, kernel density estimator. We have all these kinds of different charts that we can plot with just one single variable in the data. Isn't that like fascinating that we can make so many plots when we have just one variable data? So moving ahead from univariate analysis, we also have bivariate analysis, as I said previously. In bivariate analysis, it's something where we have a correlation between the terms in our data set. Something like height and weight. So far, we just had the height. But if we give the weight, don't you think when we plot the height versus a weight in an x comma y xy plot, there'll be some sort of relation. I would like you guys to tell me what the relationship would be within height and weight. What is the relationship when you plot height versus weight on an xy plot? Positive. Yeah. So doesn't that mean that lower the height, lower the weight, and as you go, it's going to increase. So it's going to be proportional, right? Like in most of the cases, at the very least, the majority would have a positive correlation. So as you can see, we have some kind of correlation between the two analysis, sorry, the two variables right now. So in such cases, we can do what? Since there's a correlation, we can perform correlation of analysis using the correlation coefficients. And apart from that, we can also do regression analysis. What is regression analysis? It's the same plot that you saw in the first graph, where we tried to fit a line through those plots. We were able to understand the slope of it and understand other data. That is what regression means. And this is something fascinating since with just two given variables, we are finding somewhat a good or a very insightful relationship between these data from the data set. Now, moving ahead to multivariate analysis, when we have many more kinds of data in the same data set or variables, you say, we have a much more complicated relationship, right? So how do we analyze when we go into the three-dimensional world? So far, a single variable and two variables can be just plotted in an XY graph. But from the third variable, is it really easy for you to visualize this? Can you like how do we put it and do we like project it into a latent representation and then understand that, or do we abstract it, or do we need to reduce some of the dimensions in order to understand some of the correlations, or altogether should we like ignore some of the dimensions and just look at the ones that's important? All of this will be covered under multivariate analysis. So let's go with the first kind of univariate analysis. So in this particular course today, we will be discussing about univariate analysis. So coming to univariate analysis, as I told you, I able to see the page uh, where it's written
Yes,
short and tall.
yes,
Yeah.
yes,
So we have a plot. Okay. As I told in the beginning of the class when I started, we have a plot with just a person's name and his corresponding height mentioned in the data set. All right. What can we do with this particular thing? So we have taken a line, we have just put a dot wherever we find a person at that particular height. But don't you think, okay, here we have one, two, three, and then four, five, but in somewhere here, it's the peak. Like there are so many people that you're not able to visualize or count on your own. You're like, I think there's one here as well. I never knew that. So it's really difficult when you plot something like this, right? So that's where histogram comes into a picture, where we start plotting them vertically. So we have the height here and the frequency in the form of a box plot. But however, it's a bit continuous. So it's going to look something like this. We have three people at this bin size, and then it's eventually increasing and decreasing again. So how do we determine that we need to specify this bin size to vary from 5 feet 11, 5 feet 7 to 5 feet 8? We could have put even 5 feet and 7 inches with 1 centimeter to 2 centimeters. That will be something this small. Since we have each feet with just 12 inches, we can do even 1 inch each. So we can divide this by 12 further. Is that going to give particular meaning or not? So this is a very important aspect when it comes to histogram, the bin size. Okay. Basically, I think I hope you understood what bin size is now when I mentioned that it's 5 feet 7 to 5 feet 8. So how do we select this? If we select it too small, can we understand it? Or if we select it too big, does it like make sense? What do you guys think? Which one is better? Or let's just go and select some random uh bin size and it's gonna work all together. What do you think? So this thing is more of a trial and error basis where if we have something which has a very small bin size, it's gonna make no meaning. It's almost as similar as what we saw in the beginning, except one of two of them are gonna be plotted one above the other. And it's not even something which can be interpreted that easily, right? And at the same time, if you have such a big bin size, right? What on earth can you understand from this? Like, does this have any statistical meaning? I mean, yes, like half the people are short and half the people are tall, but apart from that, does that mean show you anything about the distribution of how people have weights or heights? Or it doesn't really make sense, right? So unless you have a particular requirement to have analysis of this small intervals or this large intervals, which is the bin size, there's no logical meaning for you to do this. So we can just play around with the bin size until we have a reasonable plot where we can see some sort of a normal distribution. Usually some things such as height, weight, we see something called as a normal distribution where we peak towards the middle and then come down. And this is how most of our data is going to be represented, at least in terms of the real world. It's not always the case. We can see sometimes that it is skewed more towards the left or skewed more towards the right. But a normal distribution is something that's ideal when you take a large data set with a large number of points varying over a large amount of time. It eventually tends to reach a normal distribution. So going ahead, let me just show you uh, about the data set that we have taken to explain this. So what we are doing is students' performance. We have So our data set, it contains around eight, eight different parameters or features when we come to machine learning terms. So what are these categories? Gender, race, ethnicity, parental level of education, lunch. Lunch? Where did lunch come from? Okay. Test preparation course. Has the person studied or not? Math score, reading score, and writing score. Out of these, we can just understand that we should have some kind of relationship between math score, reading score, and writing score, right? Probably someone is good at maths but not at reading. Probably someone is good at both, or some are not good at both, right? But what are these other five different categories for? Don't you think that we can plot something against gender, something against the race, and something against the parental's education, and against whether the person had lunch or not, and then took the test, and about the test preparation as well? Yeah, so let's look into that. Okay. So since we're first looking into histograms, right, let me say how we're going to prepare our data. Right now, we have three scores, right? We have math score, reading score, and writing score. So with math score, reading score, and writing score, let's combine all of these into a single category called as the total score. So what is this total score? We just are going to sum these three. And how do we do that? We are just going to use the pandas data frame, which allows us to easily add each one of these scores. So as you saw that previously we just used pd.readcsv. I hope that we have some people who are attending from the last week's course of data wrangling, where we explained about pandas and numpy. So here, pandas.read.csv, it just is a very easy way to understand the CSV and convert it into the pandas data type, which would be a data frame. Now, by just typing data, we are able to look at the entire data set, at least an overview of it. Okay. Now, moving ahead, the total score, it's very easy to just iterate through and add each of these and create an entire new column. Data of total score will be newly created and will be appended to the right with the sum of the same values. Now, since I've explained you about histogram, when we plot these, we are going to get a graph which looks something like this. And yeah, this does make some sense, right? Because the total is going to be 300 because we had three different tests. We see that quite the few number of people are taking a very high number of score. Like they are getting 100 on 100 in all the three tests. And it's peaking somewhere towards the middle. This is what I said, a normal distribution where we have a bell curve. It always tends towards that. Okay. And however, the data is skewed towards the left, right? You see that it's more skewed towards the left than towards the right. Aren't we able to understand the distribution of how people are scoring by just seeing this one single plot? But you'll be wondering, what is this 250? What is this 300? Because I explained it was easier to understand, but if it's someone who has no idea what the data set is about, it's a bit difficult for him to understand. Okay, so what do we do for that? We can provide this kind of a heading, X label and Y label, along with our required data. So first, let's see how do we plot this using matplotlib. So for the first graph, as we had the data already set in our data of total score, it's very simple. All we need to do is have a figure with a figure size of 20, 10, which is basically the aspect ratio. We have the X and the Y aspect ratio, which is represented in fig size. So what were we doing? plt.figure with a fixed size as a parameter. When we mention this, we have a plot and its aspect ratio set. Now, once this is set, we just need to do plt.hist along with what data that we're going to be plotting. And matplotlib is smart enough to consider a bin size which is moderately reasonable for representing this data. So we can either trust this or we can go ahead and fine tune this by our own. Okay. So it's just these two lines of code after processing our data by adding the data sets, corresponding variables to get the total score. It's just the two lines, right? And we are already able to like visualize a lot of this data and have a basic understanding of the same. So why don't we move ahead and change the bin size? Don't you think that this gives us more insight about the people who are getting more marks? Before, it was just a huge block over here where we won't really know how many people are actually getting the like the maximum amount of marks and the people who are like at the 90th percentile. There's no differentiation in what the bin size that was selected by matplotlib on its own. So when we change the bin size by ourselves, so what are we doing here? We had plt.hist even the last time where we had only one parameter that was data of total score, right? When we add an extra parameter, bins equals 20, it's going to change the width of each of these. So we can also do this. We can just save it as bins of 10 and execute. But oh, this made it even worse. So just trial and error. You see that this gives a much higher understanding of how things go on over here. And when we increase it to 40, what happens? We have a much higher understanding of how each of the scores vary, right? So I think at this point we're introducing more amount of noise to this data, and it's not giving the kind of analysis that we had previously. So we just need to find where we are comfortable with the kind of data that we're getting and we're able to understand. And here we have a reasonably sized bell curve, which we would like to understand and take ahead into our analysis before performing any kind of inference or machine learning, deep learning models, or just basic statistics. This is more than enough to understand the kind of correlation that we have. So the remaining of that would be the super title. As I said, the super title corresponds to what's on the top, and the title is what comes exactly below, which explains what some more details about the super title and X label and Y label. So the X label is what comes here, and the Y label is what comes here. So when we do this, we can also mention the font size explicitly in this way, along with the title as a separate parameter. So we have plotted this. So what have we done so far? We have plotted a histogram and we have changed the bin size and we have also added some kind of information about it on the same plot using matplotlib. And this took what? 6 to 7 lines. That's it. Is it easy? What do you guys think about it? How easy is this? Is this convenient? Is this tough?
There's a question in the
Yeah.
chat. Is there an
Is
easy
there
way to change the bin size by specifying how large each bin is instead of number of pins?
in matplotlib? So okay. Over this course, we'll be talking about Plotly, matplotlib, and other kinds of visualization, where each one of them will have a different type of coding it. Okay. In matplotlib, as of now, we're going to look at the number of bits. Later on, in the upcoming classes, we'll discuss about each of the different modules which we use to represent the same data. So you will understand better in tomorrow's class regarding the same. I hope this answers. Okay. Uh, what kinds of data visualization is matplotlib best for? So we have today everything that we will be discussing. Okay, matplotlib is actually something which can visualize every single thing. It just is going to take some kind of effort. We can do the most complicated plotting with just matplotlib itself. Okay, so as you see, we are just at 7 lines of code and we are able to get such a beautiful plot. If we have, I mean, I'm not saying that more lines of code means better results, but when we know the exact parameters to tune and understand the data along the way, we will be able to make such wonderful plots and insights that almost all of the plots that's possible, right? We can do all of them with just matplotlib. Matplotlib is a bit complicated, which is why we have other modules to do the same work. It's not like matplotlib is lacking, which is why we are going to other types of like visualization modules. So matplotlib is itself very powerful. Okay, so let's reiterate to the last two questions. One was, is there an easier way to change with bin size? So this is the manual way of doing it. So either we can set a different kinds of number of bin size and just iterate through them and make all the plots together. Or anyway, it's a manual method, or the automatic one is what matplotlib suggests on its own, which I showed the drawback of in this situation. And moving ahead, I told that it's also good for all types of visualizations. Matplotlib, it's not lacking in any way. It's a powerful tool. So this would be the answer to your last two questions, Alex, I think. So can we move ahead? So moving ahead, we see that even now we can make this plot a bit better, right? So what we do is we add some edges to the same. And how do we do this? Don't you think this is little more aesthetically pleasing for us to like look into instead of just an entire block with a region of shade? So how do we do that? We do that by just specifying the edge color equals white and LW, which is the line width, okay? The width of this being 1. I think if you zoom enough, you can see that it has a border as well. So that would be the line width. Okay, so by just adding these two extra parameters to our histogram, we have a much pleasing plot of the same. Okay, now moving ahead, let's go and look at this plot. How do you think is this plot different from the previous plot? Guys, the question is for you. How is this plot different from this plot over here? Do you notice any difference? The difference is in the probability, and here we have the frequency. What were we doing? We were basically counting the number of people having a particular score, like X number of people at 120 or 200. So what is the difference from that to a density histogram, right? So when we have a density histogram, we see the same thing in terms of probabilities. By probability, I mean to say that each of these bins, right? So at 200, we used to have around 120 people over here, 120 to 130, and a little more, we have somewhere close to 125, right? Here, we are doing the same thing, but in terms of probability. What do you mean by probability? When we add this, it's going to be 1, right? Because maximum probability is 1. So here we are going to see that at 200, we have almost a 0.01 probability over here, which means it's around 1/10, right? 1/10 of the contribution is from this, and 1/10 of the contribution is from this. So initially, when you look at this, we might not know the relative probability or relative uh, correlation between each of these bar plots or each of these bins since we don't know what 120 means, right? I mean, even though it means frequency, how do they relatively like have an understanding in correlation to the data? So what we do here is we plot it against the probability. And how do we do that? We just add a single other parameter here, density equals true. Now, let's juxtapose the histograms, okay? And how are we going to do that? And what are we going to do that against, right? Why do we need to juxtapose any given plot? So initially, we had given this scores and their frequency plot irrespective of any category. As you can remember, I hope you remember, in the beginning, we had so many different categories or what you mean features when it comes to machine learning. These are something which can be having a correlation to these scores, right? Like it may have, it may not have. So let's take something like test preparation course. None. We would expect none to have a little bit lesser score than one who has completed the test preparation course, right? So what we're doing here is we're taking the gender as a variable and we're plotting the scores against each other. So how do we do that? And also, don't you see that we have flipped it along in a horizontal way? So how are we going to do this? So let me explain the code for this. So the super title is what comes at the top. And what we do now is we create a subplot. By a subplot, we have a single plot with two subplots, right? Basically, what's towards the right half is a subplot, and what's towards the left half is another subplot. So how many subplots do we have? We have two subplots. So how do we do this? We mention over here plt dot subplot 121. What does 121 signify? 1 says that a single row and 2 says two columns. So we have the row and then the column, and moving ahead we have the one again. This says that it is the first subplot among the two plots. So that's the meaning of 121 over here. Now once that is done, what do we need to do? We need to split the data into male and female. So when we do ax.hist, like how we did plt.hist previously, we used to just give data of total score. But now we're going to give data of gender, where the gender is equal to female. And from that, we are going to take the total score. So what are we doing? We're just filtering out the data where it belongs to female and then setting the orientation to a horizontal orientation. By setting it to horizontal, it'll be more interpretable. But don't you think that both are flipped on opposite sides? Female is pointing towards the left and male is pointing to the right. So how is that done? Coming back, we see that we have something called invert x-axis. So since we have set it to horizontal, we're going to have two plots which both are going to point towards the right. But when we flip it or invert it towards the x along the x-axis, it's going to face towards the left side. So that's the meaning of ax dot invert x-axis. Okay. So continuing, we have an edge color of white, the line width of 1, a z order of 1. Z order basically means this plot is going to come towards the left of whatever is having a Z order 2. So it's a relative number among the subplots. And then we have the color of the plot, the label of the plot, and alpha is basically the transparency. As you can see, it's not entirely like solid color. It's slightly transparent towards the background. You can also see this stripes passing through over here. So that's what you mean by alpha. Then you just set the title, X label, Y label, X lim, and the invert axis, which I explained earlier. Moving ahead, we have the right plot, which is exactly the same except here 1, 2, 2. What does this do? Initially, 1 is basically the number of rows, the first row and the second column. And then we have the second to signify that it's the second in the same first column, right? 1 row, and it's the second plot. So the 2 is going to mean that it belongs to the second column in the first row. And then we have to filter the data by male, take the total score. We set the bins manually to 20, horizontal. But however, in this case, we are not going to do an invert x-axis. It's going to be a default in the right side, okay? And then we repeat the same kind of parameters. Now we have x label, x lim, and x title. But what is y tick labels? What do you guys think it is? What is y tick labels? You have seen y label, but not what is y tick labels? Basically, y tick labels is, as you see, we have y label here, right? Where we have total score. There is no meaning if you put total score again over here towards the right side. So what we can do is we can ignore that. So if we don't put this, it might give some sort of a warning or an error. So when we just put white-tick labels by giving an empty array, it's not going to fill anything over here and makes it a much more aesthetic and pleasing plot, which can be understood by the people in a more easy way. So I think this is all about histograms. Do any one of you have any questions?
A quick question. When you have the empty array in the Y tick labels, why does that still keep it for females but not keep it for males?
We have the Y label for females because we need to know what this represents, right? We are basically plotting here from 0 marks to 300. Now, we need to say that this represents the total score. It's the same over here also. So we have the total score, right? So basically what I'm saying is here, we have this facing towards the right. So we have a frequency here as well as over here. So that you know that the frequency is just inverted. But in terms of the y-axis, it's the same scale, it's the same direction. So the total score from the female is going to be carried out to the same towards the right. Like the meaning of having total score here and here is going to be the same, right?
Yeah.
Yeah.
And so Y tick labels just like matches whatever is on the male side to the female side, or because you had to
So
manually remove the male side, right?
why would you have to manually? Yeah, we are removing it manually, right? By putting y-tick labels.
But that line of code, like, does that specify that it's for the male plot?
Yeah. So the 1, 2, 2, right?
Oh, okay.
The 2 is basically for the second subplot.
Okay. Got
And the
it.
1, 2, 1 is for the first subplot.
Okay.
Did you understand?
Can you remind me what the 1, 2, 1, 1, 2, 1, 1, 2, 2 means again?
Yeah. So basically, until now we had just one single plot, right?
Oh.
Now we have two subplots. These are two plots, right? Towards the left and towards right. But it's being represented in a single plot, in a single image. So what do we do? How do we achieve this? By creating subplots. When we create subplots, we need to say how many number of plots, that is rows and columns. If we need, say, 4, two on the top and 2 on the bottom, we need 2 rows and 2 columns, right? So in that case, what we can do is we can say 2, 2. I mean 2, 2. But here we just need 2. That is one single row and 2 columns, right? We have a single row of plots, single row of subplots with 2 columns of plots.
Oh, okay. So if you had like a 4 plots and you had like you were talking about the first one, then you do 2, 2, 1.
Yeah, correct. So now since we have a single row with 2 columns, it's 1, 2, and then we are referring to the first plot. So it's going to be 1 to 1. And all of these parameters are going to correspond to that particular subplot. Now, once we change the subplot to 1, 2, 2, all of these parameters are going to correspond to this 1, 2, 2 subplot.
Okay, got it.
Yeah.
Thanks.
So let's move ahead to kernel density estimators. So as you see, histogram had this kind of a representation, right? But if you think that you just want a superficial idea about the data, like you don't want to know exactly, like by setting the bins, the number of bins, and making changes to all kinds of variables, but you just want to see how the data is being distributed, we use something called as kernel density estimators. So what happens? Just why don't you think that you have a light bulb facing towards the top in each of these bits? So it's going to plot something like this, right? Like on the top, without exactly showing you what each one of these correspond to. That is going to be kernel density estimators. It runs for a different kind of bell curve is going to look something like this. Like you don't have any distinction for each of the bin size. It's irrespective of bins. It just gives you a superficial idea about how the data varies. Okay. So when we want such kind of a representation, we use kernel density plots. Now let's go back to how we do this. So kernel density estimators, right? So kernel density estimator, it's a plot which is smooth continuous curve. Okay. The smooth continuous curve that estimates the probability density function of any given data set. So towards the left, you can see like how we did the same for histogram. We're just going to have a line for that, but we're going to represent the probability density. So unlike a histogram, which uses bars, the KDE or the kernel density estimation uses a technique that spreads out each of the data point into small bump and then adds them all together to form the following curve. Okay, so it's basically like an averaged out version of the histogram, which is more easy to understand. This gives a much more clearer picture of the underlying distribution, showing where the data points cluster and whether there are multiple peaks. So we have a single peak over here, but for something else we might have two peaks. You might have two peaks like that, right? So these peaks are also called as modes. They have much more significant importance when it comes to machine learning and deep learning, but let's not get into that now. So the KDE plots are especially helpful when you want to compare distributions or see subtle patterns in the data. So in this example, I'll show you how this is helpful to compare with the other distributions. Okay, so first, before going to that, let us see how this particular plot, right? How do we do it using code? So previously we just had something called .hist. Here we are going to use SNS dot KDE plot. Okay, KDE plot stands for kernel density estimation plot, where we assign the data to our particular data and we give the x, right? X is basically this to be total score from our data set, which was previously set. So x is equal to total score. So now it knows that it has to plot the total score against the probability density. Okay. Now, moving ahead, we have some labels, that is title, X label, Y label. And then we just plot the same thing using title layout. So we have a basic graph, we have a basic plot with a line. So moving ahead, we can make the same thing little more aesthetically pleasing by filling this entire region under the curve with some sort of data, some sort of color. And we can make it to look something like this. So it's something that can be easily understood than the earlier plot. So how do we do this? We're just going to do something called as fill NA equals true. And line width, we saw that as LW previously. fill equals to 2 is more than enough for you to just fill the color in the region under the curve. Now, moving ahead, I told you, how do we compare two different KDEs? Don't you think this is more like interpretable when compared to what we did previously with the histograms, which is here? It's literally the same plot, right? But however, we cannot juxtapose the same for the female and the male plot when it comes to histogram, because it's just going to go one above the other and it's going to be a huge mess. I think here we're not able to really understand the correlation between the male and female distribution. But when it comes to the KDE, we're easily able to see that the female have a higher peak towards this place around the 225 range. They peak out there in comparison to the male, which peak out little before around 220 or 210. So we are able to clearly see that it's also the female that they're carrying out the higher percentage in marks, right? They are pushing the boundary towards the 300s more than the men. So it is much more interpretable and we can easily understand the correlation. But what will happen if we have more than two categories, like male, female? Okay, we have two now. We're able to understand. What if there are like five different categories, right? Can we just juxtapose them all one over the other? I don't think so, because it's going to make it a little more difficult to understand. So as we saw in the initial stage, we have different kinds of categories. We have gone through the gender. What if we consider race ethnicity, which is given by group A, B, C, D? So I think there are 5 groups, or yeah, I think there are 5 groups. So let's look at that. Or we can also consider parental level of education, who has done bachelor's degree, master's degree, or some random college. So let's look into that. So the first plot will be for the students who are from different ethnic groups. So when we need to plot something like the total score against each of these groups, when we juxtapose them like we did previously, it's going to make it less interpretable. So what we do is we plot them one below the other like this to have a relative understanding of how the distribution takes place. Don't you see that it's queuing towards the right a bit? Like as we go from the ethnic group A towards E, the scale, I think you would assume that it's just because we have plotted that it's going towards the right, but it's not. We do really see a pattern over here that ethnic group A has a peak at a much lower score, which is around 170, when compared to the group E, which would be having a peak at around 225. Okay. So do you see that we have a relative much better understanding about each of these ethnic groups, like distribution of the scores? Am I right? So how do we do this? So we use something called as grid spec from the matplotlib library. Now we start a plot figure which has an aspect ratio of 20:10, where 20 is the x-axis and the 10 corresponds to the y. So you can see that this is the 10 and this is the 20. Moving ahead, we have a super title. Then what we do is we take the ethnicities from our data. We had a column called race/ethnicity. So when we do that dot unique, we get the group A, B, C, D, E separately. Once we get that, we're going to sort that using np.sort, using numpy, which is going to give group A first, then B, then C, then D, then E, so that we are able to plot that in an alphabetical order. That's done by that. Now we have AXS. Until now, we just had AX, which is just a single plot, right? But now we have multiple plots. So we're going to do that in a form of an array. Now we create a grid spec, okay, which has the length of ethnicity. What do you mean by length of ethnicity? So if we have 5 ethnicities, we're going to have 5 grid specs so that we can plot one below the other, okay? So once we do that, we can set an array with 5 colors so that we can take that automatically based on which of the ethnicities we are at. Moving ahead, we have a single for loop where we go through each one of them. Okay, this is the entire for loop. We have each one of them. We are enumerating through each of these ethnicities that we had sorted previously with the index and the ethnicity. Basically, the enumerate ethnicity is going to return the index. So group A will be 0, 1, 2, 3, 4. If you know basics of Python, it always starts with 0. So we're going to get 0 at the start, and it's going to go to n minus 1. That is 5 minus 1. That's 4. So we are going to get the index and the data itself when we use enumerate. So after that, we have this AXS array, right? What we do is we append to each one of these a fig.add subplot. So initially we had created a subplot manually where we had to mention 1, 2, 1, 1, 2, 2. But here it's going to be done in a much more programmatic way where we just mention GS, which is the grid spec of index. So when we do that, see, we have given ethnicities there as well. So this will take care of the subplot numbers. Okay. So once we are done with that, we take each one of the individual plot using AX and we take out using the index from the AXS. And after this, we create an individual KDE plot for each one of these ethnicities by giving the data equals data where ethnicity equals ethnicity, which filters out the data for the ethnicity. And once that is done, we have the x equals total score so that we filter the total score and plot it towards the x-axis. And then we can do fill equals to true so that it's colored. And for that color, we can take it from the set colors that we have given in this array. Alpha equals 1 makes it solid. So 0 means it's transparent and 1 means it's solid. Then the edge color gives you this boundary over here so that you can make a differentiation where the overlap is happening. And after that, we have a line width of 2 to make that same line more distinct. I think until now we had just LW equals 1. So once that is done, we have each subplot set. And then we just are doing xlim. Okay, I think I didn't explain what xlim is previously. So xlim is basically this limit. So we have our data which starts at 0 and up to 300. But since it's a KDE, it's going to have a little bit of a much more washed out data. So the 300 is going to be pushed up to somewhere around 340. And we see that the data is mostly like starting at 50, although there might be some people with below 50 range, we're just going to represent this from 50 to 350. So that's a limit, right, on the x-axis and the y-axis. So what are we going to do there? So we're going to just make an xlim of 50 to 350. And for ylim, this is the probability, right? Once we plot it, okay, so say we plot it as it is, 1, you see that it's going to be much more small. We're not able to understand it. Or even if it was entirely 1, okay? Can you understand anything from this? No, right? Because the sum of probabilities, it's supposed to reach to 1. When that's the case, is it making any sense to plot the y-axis from 0 to 1? It doesn't, right? So we have to set a suitable scale, and that's going to make it much better, and you'll be able to understand it in a much easier way. So that's the significance of setting the xlim and the ylim. And then moving ahead, we go and we see if the index equals to len of ethnicities minus 1. So in such a case, we set the x label equals total score, font size equals 18, and font weight equals bold. So what is that? For the final plot, right? For the final plot, we're going to set the x label. So we don't need to mention the same thing for anyone else, right? Because that's just going to be not pleasing to the eyes to just have text score, total score in the middle over there. So once we reach the end, we're going to set the x label. And for everything else, we're going to set the x tick labels as an empty array so that we do not have anything for those. Then we set the y tick labels for everything, set the y label, take params of grid alpha with the label size. We patch the alpha equals 0, and we have spine, which is top, right, and left. We have set visible equals false. So it doesn't show that grid over here towards the left and the right? So that this looks much more better. Now, moving ahead, we have just a spine of bottom. You can see that we have this line, right, at the bottom, but not in the sides. So that's the meaning of the spine. And we set the color from the index based on whichever color it is. And the text is being done here. So once we do gs.update with a headspace of -0.6, we get the exact plot like this, which allows us to compare the entire set of ethnic groups against the total score. Okay. Anyone has any doubts? Okay. So
I
yeah,
do. Are the like names of the groups automatically named just group A, group B, group C, group D, or is it somewhere in the data set?
it is there in the data set. So
Oh.
as you can see in the start, we have the race and ethnicity. The group A, B, C are taken from here.
Cool.
So what we do here is, in the beginning, we are taking race of ethnicity dot unique. When we do dot unique, we get to know that there are just 5 groups over here. And against each one of these groups, the data is going to be segregated and plotted.
Okay, got it. Thanks.
Yeah. Okay, so let's go ahead. So let's make this a plot against two categorical features. So what did we see? Group A, B, C, D, E against total score. But what if we do the same, but we have for math score, reading score, and writing score separately? Don't you think we have much more insights in it? I mean, if it's required, we can plot the same thing. Basically, it's the same plot where instead of the total score, we are plotting individually for each one of these different kinds of scoring, right? So how do we do this? The code most probably, like it to the most level, it remains the same towards the top. But however, here we have two for loops, right? Because we have a grid spec where we are plotting three separate kinds of categories along the x-axis, which is why we are setting the grid spec size as the length of ethnicities, which is 5 towards the y-axis and 3 towards the x-axis, right? So we are going to have length of ethnicities comma 3. Now once that is done, think of this like a matrix. So this would be a 5 row and a 3 column matrix. We need to enumerate through that, right? So we have two for loops. That's how we iterate through any matrix. And after that, it remains mostly the same. We have the creation of the plot, setting of the X labels only for the last one. And then for the others, we do X tick equals X tick labels and give a empty array. And we set the other parameters as it is. So I think it's quite straightforward. So when we do this, we're going to get a plot where we have against multiple categories for multiple ethnic groups. So you can see if there's multiple peaks, like here it's tending towards a peak over here, a mode. And in the other case, it's just a bell curve, right? I think I told initially that things tend to be like more concentrated towards one side when we take a large enough data set. And moving ahead, we can do the same thing against the score of students with parental level education, where we have three different types of parental education, that is bachelor's degree, any college, master's degree, associate's degree, high school, some school. So we are plotting the math score, reading score, and writing score against each one of these. So the code will remain the same. It's just that you change the length of ethnicities to education, filter out in the same way. Okay. So the code remains the same. And moving ahead, let's look at box and whiskers plot. So what is box and viscous plot? Do you guys remember? I think most of you would have. So basically, it's a box representation where you have a box where the line inside shows the median, which is basically the 50% of the entire data. And the top of the box and the below of the box represents the Q1 and the Q3, that is the interquartile range. So basically, Q1 corresponds to the 25th percentile data, and the bottom line is the 75th. Or in other terms, since the middle line is a 50% line indicator, the above line would be 25% above the median, and the bottom would be a 25% below the median. It goes towards the 100%. And we have this line which goes to the other ends from 0 to 100. Okay. And we have the outliers outside this plot. We may include it or we need not include it. Okay. So basically this is a box plot. Now, when it comes to a box plot, the first quartile, as it is, as I said, this would be the 25th percentile, the median is 50th percentile, and the third quartile is the 75th percentile. And this end over here would be the maximum, okay, and this would be the minimum. And if any outliers are there, they are plotted as individual points. In this case, it's not being plotted here, but they will be plotted outside this as individual points. So let's go to how this is going to be plotted. Figure is equal to PLT figure with the aspect ratio SNS dot box plot. That's it. It's as simple as that. Where we give X as the test preparation course and the Y as the math core. So here we see that initially we saw that people had some people had completed the course and some people had not, none and completed. So when you can see that when we visualize the same thing, okay, you see that those who have completed the course tend to have a much higher median than those who have not. This does not mean that people who did not prepare using the course did not get the 100. Even they got, as well as the people who have completed the course got, except the fact that those who completed the course tends to have a lower number of people towards the lower marks, and those who didn't prepare using the course, they tend to have a higher number of people towards the lower marks. So don't you think that we get a lot of insights when we do a box plot regarding how the distribution of the data is with regarding to the quartile ranges? That's the first median and the third quartile with the maximum and the minimum and the outliers. So a box plot basically represents each one of these aspects by just using these two lines. And we have a set title and then the tick params, Y label and the X label. So the code wise, it's quite straightforward. And moving ahead, let's go to violin plots. So violin plot is the same, or it's trying to make the box plot much better. Okay. Can you see this page where I'm showing the violin plot with
Yes,
the recovery
yes.
time? Yeah. So the violin plot, it combines a summary statistics of a box plot with the shape awareness of a KDE plot, kernel density estimator plot. You're like, we just finished that long time back. Why is that even used here? So you see that here in the center, we have a box plot, but on each side of that box is a mirrored kernel density estimator curve. Like just cover and see towards the left side. This is basically how the data would look if we did a KDE plot for the same. So this is a mirrored image. What's there towards the left is going to be mirrored to what's there towards the right. So giving it a shape similar to a violin, don't you think it looks like a violin? This makes violin plots very powerful for visualizing both the summary and the distribution shape of the data, since the box plot does more of the work for the summary and the distribution shape is done by the KDE part of it. So they're especially useful when comparing several groups and when you want to spot patterns like skewness, right? So you see that it's a sharp peak over here, but it's skewed towards the right. So when you want to spot something like skewness or multimodal distributions or data concentration zones that a box plot alone might miss. In such cases, we can go with a violin plot, okay? So in such a case, what we have taken is the same thing that we have done above, where we have none and completed course preparation, but with the help of a violin plot. It's the same thing, the math score against none and completed. So when we look at this, as I told you previously, we are supposed to have a box plot, which is here. You can see that this is the medium. This is the 75th percentile, the 25th percentile, min max, and the outliers as well, right? The outliers are also being plotted using the KDE. But however, KDE will just push it a bit over. That's why it's going below the 0 mark, which means that someone have come to 0 as well, okay? So don't you think that this is a much better representation when compared to a box plot, where we just see what the median and the quartile ranges are? We don't know how the data is distributed, like where the peaks are. I mean, median does mean there's a peak over there, but doesn't mean we can see any distribution apart from that, right? So in such a case, the violin plot is going to be much more useful to understand the data. So in
Yes.
terms of code, we have a violin plot where the X has a test preparation course it's the same as the box plot. Basically, it's the same as the box plot in terms of code, but instead of a box plot, we're just going to put a violin plot. So I think that's quite straightforward. Do you have any doubts regarding anything that's been discussed?
I had a question about why you can't see the quartiles in the violin plot you just plotted.
The quartiles are here, right? It's too small. That's the thing. This is the quartile.
Is that just automatic?
Yeah, this is automatics. Like you can see that the box plot ends here. This is the third quartile. This is the median, and this is the first quartile,
Okay, got
which is within. I mean, this is what I showed you previously. Here was an exaggerated version, but when it comes to real-time data, it is sometimes out of scale. So we need to do some pre-processing in order to do and fix all that, which can also be fixed from the code itself. So in this case, which this is the default one. So anyone else? Do you have any doubts? The course is coming to an end, so that's it in terms of content. That is it for today's course. Tomorrow we'll be going to the next topic, and I hope to see you tomorrow.